All right, good morning, everyone. So welcome to lecture 18 of 124-104. This is also our last lecture before the break. Of course, you still have the workshop tomorrow, so I'll still see you. But today we will talk about static equilibrium. We'll try and solve situations where we want an object to be in static equilibrium. So we want to determine the forces that are acting on this object. So we're sort of like combining what we've learned before about net force equals zero and torques as well. But before we go to the problem solving bit, just a few definition of terms. Static equilibrium, it's all about maintaining something at rest. So static means that the system is at rest relative to everything else in the system. And so if we want to achieve static equilibrium means that the net torque is equal to zero, so that, you know, as we've learned, torque causes the object to rotate. So if the net torque or the sum of all the torques acting on the object is zero, then the object will not rotate. And also during equilibrium, the net force must be zero. And we learned from Newton's second law of motion that net force creates acceleration. So if there is no net force, then the object will not accelerate, and therefore it will be in static equilibrium. So therefore, coming from the definition of static equilibrium, we need therefore to satisfy these two conditions. Net force is equal to zero. Remember that force is a vector quantity. So if you have a diagonal force, then the net force along the horizontal should be zero, meaning the total force pointing to the right should be equal to the total force pointing to the left, right? Net force along the horizontal is equal to zero, and the net force along the y should also be equal to zero, meaning upward forces, the total upward forces should balance out the total downward forces in order to have net force being equal to zero in all axes, and therefore acceleration is zero. So also net torque is equal to zero means, you know, we've defined torque to be either clockwise or anti-clockwise, to achieve either clockwise or anti-clockwise rotation. So net torque equals zero essentially means that the total clockwise torque should be equal to the total anti-clockwise torque. So we need to balance out the torques about a chosen pivot in order to have no rotation in the object. All right, so this is what we'll be doing today, balancing out forces and balancing out torques. Remembering, of course, that for torques, the important thing is to find the moment arm. Just a reminder, when we say lever arm or moment arm, this is this distance where you draw from the force to the pivot point, right? And the moment arm should be perpendicular to the force. So so I know yesterday we talked about three-dimensional torques, right? And we used vector or cross products to find the torque by a three-dimensional force and three-dimensional moment arm. But for static equilibriums, we'll just confine ourselves to two-dimensional forces. So finding the moment arm should be relatively more straightforward than three-dimension. You just draw a line which is perpendicular to the force, and that gives you the moment arm. Knowing the moment arm and the force allows you to calculate the torque. Right, so to find the moment arm, so notice there are two things you need to determine the moment arm. You need the force and you need the pivot point. So you measure the moment arm from the force to the pivot. So when we're solving problems involving, balancing of torques, Of course, it's important to draw the free body diagram because that shows you all the forces acting on the object. But the most important bit is picking the pivot point. So the choice of pivot is arbitrary. It's totally up to you to choose the pivot. And hopefully at the end of the lecture, you'll have the skills to choose wisely where you will put the pivot point, which will allow you to calculate the network. Some things to remember is that the center of mass, the weight of an object acts at its center of mass, and we've already learned, center of mass. If it's a geometrical object, center of mass is at the geometric center. Right, and the choice of pivot is important because at the pivot point, there is no network. The forces will not contribute to torques at the pivot point. So a good tip will be to choose your pivot where you have unknown or uninteresting forces, because then if you put your pivot at the position of an unknown force, you eliminate this unknown force and you don't have to worry about this unknown force. Right. So I guess the best way to look at this problem solving is like a recipe here that I've listed down, is to look at problems, right, and try solving them. So let's try to start with first an easy problem here. You have a plank, could be plank of wood, which has a mass of 25 kilograms. It's suspended by 2 strings, shown by these black vertical lines, and we want to find the tension in each string. Okay, so the plank has a length of L. The string on the right here is located a quarter of the length away from half of the plank's length. All right, so the first step, if you're given this situation, is to draw a free body diagram, okay, so that you know all of the forces that are acting on your object. And hopefully by now we know that there should be a weight force. Any object that has mass should have a weight force. Where should we put the weight force? So the center of mass, which will be at the geometric center somewhere here. Right. And you have strings. Whenever you have a string pulling on an object, we've learned that tension is present, and tension is always directed away from the strings. So you have tension 1 for this string here pointing upwards, and tension 2 for the other string, which is also pointing upwards. All right, so one important thing to notice when you're drawing the free body diagram for static equilibrium, you need to put your forces at the exact point where they are acting. Okay, and so the weight was drawn at the center of mass, at the middle of the plank, and the tension forces were drawn where the strings are located. I know when we first learned about the free body diagram for net force is equal to 0, Newton's second law of motion, we can draw the free body diagram as just coming from a single point, so that weight force is here, tension 1 is here, and tension 2 is somewhere here, right? When we did free body diagrams using Newton's second law of motion to find net force is equal to 0, we can just draw our forces originating from a single point, maybe from, and just represent all the forces. And that's fine for when you find net force is equal to 0. But if you want to use net torque is equal to 0, then it's really important to draw your forces exactly where they are acting, because then you'll need to measure moment arms, and so the location of the forces are important, right? Okay, so once you've drawn your free body diagram, we can simplify this. I'll just calculate the weight now because I know the mass. So the easiest thing for me to do is to calculate the weight force. Weight is equal to mg, 25 kilograms times 9.8, gives me a weight of 245 newtons. Right. Then the next step is to pick a pivot. Right? If we were to balance the torques or acting on this plank, we need to choose a pivot. It's around this pivot, about this pivot that the plank will try to rotate. And here you have three forces, T1, T2, and weight, which means that you have three choices for the pivot. You can choose to put your pivot at the position of T1, T2, or weight. Okay. Just remember that the force at the point where you put the pivot gets eliminated. So in this case, which will be a wise choice for the pivot? Yeah, so it will be either T1 or T2. You're right. It doesn't make sense to put the pivots at the center of mass where the weight force is, because then you eliminate the only thing that you know, which is the weight force. But you have two unknown forces, T1 and T2. So if you put your pivots at either T1 or T2, then you eliminate one of the unknown forces. So as we've suggested, let's put the pivots at the position of T1. Okay, so putting the pivot at the position of T1 eliminates the force T1. And therefore, you only have these two forces, T2 and the weight force, which will try to rotate the plank about the chosen pivot. Okay. So then you can balance the torques about your chosen pivot, remembering that to balance the torques, the clockwise torque should be equal to the anti-clockwise torque. Right, so looking at your free body diagram, which force will try to create a clockwise torque? Is it weight or T2? Weight, right? So weight, it's pulling on the plank downwards. So if the plank were to swing downwards, it will rotate about the pivot point in the clockwise direction, right? And so the clockwise torque will be equal to, torque is equal to moment arm times F. So that will be equal to the moment arm of the weight times the weight force. Okay. For force T2 is pulling the plank upwards. So if force T2 were to pull the plank upwards, the tendency of T2 is to rotate the plank around the pivot in this manner. So this will be an anti-clockwise rotation that will happen if T2 were to pull the plank upwards. So your anti-clockwise torque will therefore come from T2. So that will be the moment arm from T2 times the force T2. Right. Okay, so we need to determine what are the moment arms RW and RT2. So the moment arm, you draw that from the force. It should be perpendicular to the force and passing through the pivot. So that means that's perpendicular. So this means this will be the moment arm for the weight force, which is L/2 times the weight force. Moment arm for T2, also the force T2 is here. You draw your moment arm perpendicular to the force and passing through the pivot. So therefore, this will be the moment arm for T2. So that will be L/2 plus L/4 as the distance times T2. Right. Okay, so we can simplify our equations now to solve for T2. We want to find T2, so therefore, so all the L's can cancel out. L appears on all sides of the equation. Right, so you have 1/2 weight is essentially 1/2 plus 1/4 T2. This one is 3/4. Okay. So you have 1/2 times 4/3 weight is equal to T2. Right. Okay, so T2 will therefore be equal to 2/3. Yeah, 2/3 times the weight force, which we've calculated earlier. 2/3 times 245 gives us T2 163 newtons. Right, are we okay with this solution? So it's, yeah. All right, so we have just balanced out the torques about the chosen pivot. Clockwise torque should be equal to anti-clockwise torque. Right. So as we said, the choice of pivot is arbitrary. It's totally up to you to choose the pivot point. So in this case, we chose T1, the position of T1 to be the pivot point. But there is nothing stopping you from choosing T2 as the pivot point. So if you put the pivot point at the position of T2, then you're essentially eliminating T2, and the two forces you have are T1 and the weight. So you can also balance out the torques about the pivot at T2. So again, clockwise torque should be equal to the anti-clockwise torque. Right, this time T1 will pull the plank upwards, and the tendency of that is to rotate the plank around the pivot or about the pivot in the clockwise direction. So T1 will provide a clockwise torque, whereas the weight force will pull the plank downwards. So the tendency of the weight force is to rotate the plank about the pivot in the anti-clockwise direction. Right? So we can then again balance out the torques. Moment arm of T1 times T1 equals moment arm of the weight force times the weight force. Okay. So as before, T1, the moment arm of T1 measured from the pivot is this length here, RT1. So this will be L/2 plus L/4 times T1. And the moment arm for the weight force is drawn from the weight force to the pivot point. That's a 90-degree angle there between the moment arm of weight force and the weight force. So this will be L/4 times weight. Right, so the weights will again cancel out. So you have 3/4 times T1 is equal to 1/4 times the weight, or T1 is equal to 1/3 the weight, or 1/3 times 245, 81.7 newtons. Yeah. Oh, for the L's, yeah. Okay, so L/2 plus L/4. Yeah, let's just remove the T's and W's and just work with L's. Yeah, L/4. So L appears in these two terms here, so we can factor L out, and that will just be 1/2 plus 1/4. Factoring L out here, if you distribute L to each of the terms in the parenthesis in the bracket here, you recover this term here. So L times 1/2 is L over 2, and L times 1/4 is L over 4. So you sort of can factor out the L. L appears on the left side and L appears on the right side as well. Yeah. So is that, yeah, okay. Cool. All right, so we have now determined T1 and T2 by balancing out the torques. You don't always have to do balancing torques twice. You can also use the balancing of forces, net force is equal to 0. So once you've determined T2, right, by putting the pivot at T1, we were able to determine T2, 163.3 newtons. And then there's only one force that's not known, which is T1. You can then do balancing of forces, meaning net upward force should be equal to the net downward force, right? So the only there are two upward forces, T1 plus T2 should be equal to the weight force, okay? Or T1 should be equal to the weight force minus T2, okay? And we know we've calculated the weight force 245 newtons, and by balancing the torques about T1, we were able to calculate T2 163.3. So we are able to find T1, it's also 81.7 newtons. Right. Yeah. Okay. So usually if you have only one unknown force left, balancing of forces can be used to determine this only unknown force. Right. Any question about how we solve this problem? Because yeah, how we did it is essentially a recipe that you can apply to any sort of equilibrium, static equilibrium problem, and it should hold regardless of, you know, how complicated the problem is. Yeah. So are we happy? If we're happy with this solution, then let's try to consider something a bit more complex, so an average, yeah, average difficulty problem. You have here a sign. This sign has mass M, 2.5 kilograms. It's hung 1 meter from the end of a long beam. So this beam here has a length of 4 meters, and the mass of the beam is 400 kilograms. The beam is hinged to a wall. Okay, so this is the hinge of the beam to the wall, and we want to find the tension in the wire. So this is the force that we want to find, tension on the wire. Right. Usually it's easy. Let's do the easiest things. Yeah, this will automatically probably land you 1 or 2 marks in the test. So we know the masses, mass of the sign and the mass of the beam, so we can straightforwardly calculate for the weights. So the weight for the sign will be the mass of the sign, 2.5 times 9.8. That will be 24.5 newtons. And we can also calculate the weight of the beam. The mass of the beam is 400 kilograms times 9.8. Gives you 3,920 newtons for the weight of the beam. All right, so we want to calculate the tension T. We know weight of the beam, we know weight of the sign. We don't know the tension, and we don't know the forces exerted by the hinge. The hinge exerts a horizontal and vertical force as shown in the diagram here. So because we don't know more than one force, we need to do balancing of torques to solve this problem. We only do balancing of forces if there's only one force that we don't know. But if we don't know more than one force, then balancing of torques will be will be the solution to use, because then we can eliminate some of the forces we don't know. So to do balancing of torques, we need to choose a pivot point. So pick a pivot. Right. So in this case, which will be the most sensible position to put the pivot at? Remember that the point where you put the pivot is the point where forces are eliminated. So you have 1, 2, 3, 5 forces, but essentially you have 1, 2, 3, 4 positions, 4 choices of where you can put the pivot point. Where will be the most sensible place to put the pivot? Yeah, so if you put the pivot here at the wall, at the hinge, then you eliminate these 2 forces, the force due to the hinge, right? And these immediately you eliminate 2 unknown forces. So it's most sensible to put the pivot at the hinge. Right, so yeah, so putting the pivot at the hinge. Okay. That eliminates the forces on the hinge. And if you want to redraw your free body diagram so that it's cleaner, so I've redrawn the free body diagram here. You have the beam, and then you have tension force at some angle 30 degrees relative to the beam. You have the weight force acting at the center of mass, and you have, weight force of the beam acting at its center of mass, the middle, and the weight force of the sign acting, 100 meters away from one end of the beam. So you don't have to worry about the forces at the hinge, FHY and FHX, because you've put your pivot at that point, and so you eliminate FHY and FHX. Cool. All right. So you have this free body diagram. I just copied over to the next page. It's the same free body diagram with the 3 forces left there. Notice that the tension force is a diagonal vector. It's at an angle 30 degrees relative to the horizontal. And I hope that by now, whenever you see a diagonal force, it's your first intuition is to break this down into horizontal and vertical components. Yeah, so you can break down the tension force into its vertical and horizontal components, Ty and Tx. Okay, so if this is 30 degrees, then this angle is also 30 degrees. So therefore, Tx will be equal to T cosine 30 degrees, and Ty will be equal to T sine 30 degrees. Right, so we still don't know what T is, and therefore we still cannot solve what Tx and Ty are. But then by breaking down this diagonal vector into vertical and horizontal components, we can see that only the vertical component actually contributes to the torque. All right, your chosen pivot is here. Notice how Tx will pass through your pivot, so there's no way for us to find a moment arm for Tx, but for Ty we can find a moment arm because we can draw a line perpendicular to Ty and passing through the pivot. So therefore the horizontal component of Tx will contribute 0 torque, and we only need to consider the vertical component Ty. Right, does that make sense? Okay, so by realizing that we can further simplify our free body diagram, we can get rid of the diagonal force, and the horizontal force doesn't contribute to the torque. Only the vertical force contributes to the torque. And of course, the weight forces contributes to the torque as well. So we can then balance the torques about the chosen pivot. As usual, clockwise torque should be equal to anti-clockwise torque. right? Looking at your free body diagram, the weight forces will tend to rotate your beam about the chosen pivot in the clockwise direction. Okay, so for clockwise torques, you have two forces contributing to clockwise torques. So you'll need the moment arm of the beam, the weight of the beam times the weight of the beam, plus the weight of the sign will also contribute to the clockwise torque. So you need the moment arm for the weight of the sign times the weight of the sign. So those are the two forces contributing clockwise torque. Whereas the tension force, the Y component of tension force, the tendency of that is to rotate the beam about the pivot in the anti-clockwise direction. So then that will be a torque of moment arm due to the Y component times the Y component. All right, so we know the values, we can substitute them. So moment arm from the weight of the beam, it will be this. Yeah, so that will be 2 times the weight of the beam, 3,920, plus the moment arm for the weight of the sign. So if you draw a line perpendicular to the weight of the sign to the pivot point, the moment arm will be 3 meters, right? It's 2 plus 1. So that will be 3 meters times the weight of the sign, 24.5. And for the Y component of the tension, you draw a line perpendicular to the tension and passing through the pivot. So this will be the whole length of the beam for the moment arm. That will be 4 times Ty. Right? Okay, so then we can solve for Ty. It will be this 2 times 3,920 plus 3 times 24.5 divided by 4. You should get 1978, about 0.375 newtons. Right, so what you've calculated by balancing the torques is just Ty. What we want to find is T. So if we want to find T, we know that Ty is equal to T sine 30, therefore T is equal to Ty divided by sine 30 degrees. Right, so T should be equal to 1978.375 divided by sine 30 degrees. That should be a tension of 3956.75 newtons, or you can round this 3960 newtons. Right. Are we happy with the solutions? Did that make sense? Yeah. So again, we just systematically applied, the steps of drawing the free body diagram, picking the pivot, and then balancing out the torques about the chosen pivot. Right? Cool. All right, let's see how our method stacks up to this ladder problem. Ladder problem is probably the most difficult we can ask you. Oh, I don't know. Maybe you can check the worksheet questions tomorrow and you can tell me whether the ladder problem is more difficult than the one in the worksheet tomorrow. But yeah, so here you have a ladder that's leaning against the wall at an angle of 30 degrees. The ladder has a length of 3 meters and it has a mass of 1.5 kilograms. And then you have Homer who's climbing up the ladder here, and he probably stops about a quarter of the way up. So that's length over 4. Homer has a mass of 60 kilograms. Okay, if the ladder were to stay in equilibrium so that it will not slip, there should be a frictional force between the ladder and the floor. Okay, and what we want to find is the minimum, is the coefficient, essentially the coefficient of static friction that's needed to prevent the ladder from slipping at the base, so around here. Okay, what should be the coefficient of friction between the ladder and the base so that the ladder will not slip and the ladder and Homer will remain in static equilibrium in this condition? Right. Okay, so first step, draw a free body diagram. Okay, what are the forces acting on the ladder? Any force? Friction, yes, what's the direction of friction? Is it, yeah. If the ladder were to slip, yeah, if the ladder were to slip, the ladder will slip in this direction. Right? Okay, so friction should oppose this potential slipping of the ladder. So friction should be directed opposite to where the ladder will slip. Right? Does that make sense? Yeah. Okay, any other force? Yes, weight. There are two weight forces, weight of Homer and weight of ladder. Good. Any other force present? Normal force. Normal from, yeah. So the wall is supporting the ladder, so there should be a normal force. Normal force is always perpendicular to the supporting surface. So you have this horizontal normal force from the wall, and of course from the floor it's vertically upwards, perpendicular to the floor. And you have the two weight forces. The weight force of the ladder should act at its center of mass, which we can consider to be at the middle, L/2, middle of the length, and Homer is quarter of the way up the ladder. Okay, so these are our forces. Right now, yeah, before we do balancing of torques and all of that, because we know, you probably will think that we need to balance torques, and that is correct because we don't know 1, 2, 3 forces. We only know these two forces. And we can actually calculate those forces that we can easily calculate. The weight of Homer, this 60 times 9.8. I did the calculation earlier, so we'll, yeah, 588 newtons, and we can calculate the weight of the ladder, 1.5 kilograms times 9.8 meters per second squared is 14.7 newtons. Right, so we know these two forces, we don't know 3 forces. So yes, we will use balancing of torques in order to eliminate some of the unknown forces. But to help us find, help us find where to put the pivot point, first, let's go back to what we need to solve in the first place, right? We need to solve for the coefficient of static friction, mu sub s. And coefficient of static friction comes into the definition of frictional force, right? Friction is defined as the coefficient of friction times the normal force. And it should be the normal force on the ground because that's where the friction comes in. So for us to know the coefficient of friction, we need to be able to find the frictional force F. And we also need to find the normal force by the floor NF. Right, so looking at your free body diagram, is it possible to determine either friction or NF without doing balancing of torques? Yes, yeah, if you look, NF is pointing upwards, WL, WF are pointing downwards. So we sort of, yeah, when you're doing net forces, you separate horizontal and vertical forces. So we can, in fact, indeed balance out balance forces. Net force is equal to 0 to find NF. Yeah, so net upward force is equal to net downward force. As Glenn said, NF should be equal to the weight force of the ladder plus Homer. Right. So we are able to find NF. Okay, if we balance out the forces along the horizontal, say net force to the right should be equal to the net force to the left. Then there are only two forces along the horizontal. Then we know that the friction force should be equal to the normal force provided by the wall. Right, but it's not really useful because we don't know either the frictional force and the normal force provided by the wall. So that sort of gives us then a clue that if balancing of forces, net force is equal to 0, makes us hit a wall and we're stuck, then maybe balancing of torques will be the next step. Right, so if we balance the torques, maybe we can balance torques to find either F or NW, because if we find either of them, they're equal, and that will allow us to solve for the coefficient of friction. So we have here the frictional force and the NW. Which point will be the most sensible point to put the pivot in this case? Right. So you don't know F, you don't know the frictional force, and you don't know NW. Right? You can put the pivot at either the position of the frictional force or NW, because then if you put the pivot at either point, it eliminates one of the unknown forces, F or NW. Okay. Right? Where will you put the pivot? Yeah.
If you put the pivot at F, would it also like cancel out the ovals?
Yes. So whenever you put wherever you put the pivot, it cancels out all the forces at the pivot. So you have two forces where the frictional force is, and one force where the NW force is. So if you put the pivot where the frictional force is, then you cancel these two forces. Yeah. And then you don't have to worry about these two forces. And so maybe it's more sensible to put the pivots at position of the frictional force. Okay, so putting the pivot where the frictional force is, you can redraw your free body diagram. Okay. And so you can eliminate all the forces that are at the pivot. So you only have to consider the weight force due to Homer, the weight force due to the ladder, and the normal force from the wall. So you can balance torques about the chosen pivot here at the floor. So as usual, counterclockwise torques should be equal to the anti-clockwise torques. Okay. So look at the forces one by one. The weight force due to Homer is pointing downwards. So the tendency of the weight force is to rotate the ladder about the pivot in the clockwise direction, right? And similarly for the weight force of the ladder, the tendency is to rotate the ladder about the pivot in the clockwise direction. So there are two forces contributing to a clockwise torque. So you have there the force of Homer's weight, and torque is equal to moment arm times the force plus the weight force of the ladder. So these are the two forces contributing to the clockwise torque: weight force of Homer and weight force of the ladder. And of course, torque is equal to moment arm times the weight. So you have moment arm of the weight of Homer and moment arm of the weight of the ladder. Anti-clockwise torque, if you look at the normal force about the wall, the tendency of this normal force NW is to rotate the ladder about the pivot in the anti-clockwise direction. And so therefore you have the moment arm of that normal force times the force NW. Right? Now, determining the moment arm will be from the weight force of Homer. It will be aligned perpendicular to the weight force and passing through the pivot. So this will be the moment arm of Homer's weight. Similarly, for the weight of the ladder, the moment arm is perpendicular to your weight force to the pivot. So this will be the moment arm of the ladder. The ladder is leaning at 30 degrees angle to the wall. So if that's 30 degrees, then this should be 60 degrees. And that allows us to find the moment arm. This length here is the moment arm for WH. And this length here is the moment arm for WL. So RWH will therefore be the hypotenuse here, 0.75 times cosine 60 degrees, right, times the weight of Homer, 588 newtons. Okay. Plus the moment arm of WL, it's this length here, so that will be half of the ladder's length, 1.5 times cosine 60 degrees times the ladder's weight, 14.7. That will be equal to, so this is the clockwise torques with the moment arms and weights. For the anti-clockwise torque, we need to find the moment arm of NW. Again, if this is NW here along the horizontal, moment arm should be perpendicular to NW and passing through the pivot. So the moment arm for NW will be the green line here. And so the green line can be solved as the hypotenuse, which is the length of the ladder, 3 meters times sine 60 degrees times NW. Right. Does it make sense how we determine the moment arms? Yeah. Okay. Because I think, yeah, that's probably the crux of the problem here. Once you've determined the moment arms, then you can solve for NW. Yeah. And once you know NW, Then you also know frictional force, because frictional force is equal to NW 89.114 newtons. And therefore, you can solve for the coefficient of friction. So coefficient of friction is equal to frictional force divided by the normal force provided by the floor. So that's 89.114 divided by the NF we solved earlier was 602.7. Right, so you are able to solve the coefficient of friction 0.148. Right, did we follow the solution to finding the coefficient of friction? Are there any questions? So hopefully you will be able to do the assignment. Like the online assignment has a question about the ladder. So it's, yeah. So I will expect then that all of you will get the assignment question correctly, yeah? Right, but yeah, if there are no questions, this essentially ends our lecture on static equilibrium. And tomorrow we'll have the last workshop before the break. So I'll see you in the workshop tomorrow, and have a good day, everyone.